This is undoubtedly the right solution. Where's the,
should be one on the other side. There should be two of them.
oh, thank you. Okay. And don't do that. Oh, sorry. Come on. There you are. Okay. Good morning. We apologize for the brief delay in getting started. If you arrived just in the last few moments, you missed out on the opportunity to stand out in the hallway waiting for the door to be unlocked. It was a real pleasure. The company was very good. So this is the first session of the ISDC 2014 Space Solar Power track. Your organizers are Gary Barnhart and myself, John Mankins. We are certainly glad to see you this morning. Before we begin with an introduction, we have a special announcement by National Space Society, XCOM, Grand High Poobah, Mark Hopkins. Be sure to speak into the microphone.
Oops.
Where's your hat?
Good question. A lot of things are missing these days. I have a very special award to give today, and this award goes to an individual who's Japanese, because Japan has been by far the leader in space solar power research in the free world. And secondly, this individual has demonstrated a considerable amount of expertise in finding lost Americans in Japan, and also in numerous social occasions involving the space solar power community, has lubricated these activities with a certain amount of alcohol. So the first and perhaps only annual ISDC award, special award, the Saki Award, goes to Professor Nobukaya. You want to get your award? We'll make a comment.
Yeah, thank you very much. I have very honor. Yeah, I'm surprised. Yeah, Gekikam. Yeah, I like it. Please enjoy everyone. Yeah, thank you.
Are you just going to look, John? I wouldn't trust him. I plan to return the bottle.
Oh,
The bottle would be as nice as it was when I got it.
I'm sure about the bottle.
Well, congratulations, Professor Kaya. Certainly well deserved. But you should have brought one for the whole class. Okay, so with that, let me go ahead and get started and see if I can't get us a little bit closer to being on track. So I think you know perfectly well what is space solar power. It's the idea first invented by Dr. Peter Glazier in the 1960s of placing large systems, large platforms in space to harvest the energy of the sun and deliver that energy 24 hours a day, 7 days a week to locations on the Earth. A part of the vision of space solar power is that such platforms located, for example, in geostationary Earth orbit would be capable of delivering power to a wide variety of locations on the Earth below. So this just illustrates for a platform that might be located at the equator, just off the western coast of South America, that such a platform could, in principle, deliver power to most of North America and South America, or South America. Now, obviously not simultaneously, but the key point being that one such platform could address upwards of the energy needs. Oh, thank you. The energy needs of upwards of 600, 700 million people. Similarly, an SPS placed at the equator over the Indian Ocean could provide power to markets reaching from Central Europe to northern Russia, most of China, India, sub-Saharan Africa, from a single platform. And this is a unique feature of space solar power as opposed to ground-based solar power, because obviously ground-based solar power systems are where you put them. Whereas and although you could tear them down and relocate them, this is a challenging and expensive operation. In the case of space solar power, the vision is that one would be able to serve a very large market from a single platform. And this provides a critical opportunity for entering into the future energy marketplace for space solar power. I'm not going to talk at length about the system concepts. I have another talk this afternoon that will focus on those. What I did want to just mention this morning is a little bit about the changing pathways that we have envisioned for how space solar power might be realized, including not just the technical concepts, but also the programmatic concepts. So this is the 1979 reference system. This emerged out of a series of studies by the Department of Energy and NASA and a variety of aerospace industry participants. And it envisioned a large conventional three-axis stabilized platform in geostationary Earth orbit, launched by large two-stage reusable heavy lift vehicles, put together in space by large in-space factories involving thousands of robots and hundreds of astronauts, and delivering power to specific locations on the ground in principle. In this study, only in the US. And the roadmap that was tentatively framed to go and accomplish this was essentially a vast version of Apollo. And so what you have over in the first few years would be the concept development and evaluation program, the thing that was done in the late 1970s, then a decision point to proceed. And this is kind of a log scale in terms of funding and time. And then there would be phase one, where you'd go forward and you'd do the preliminary development of all of the key systems, the launchers, the ground systems, the space factories, all in one vast project. And at the end of this, you get some decades later and some literally hundreds of billions of dollars later, you would have the first solar power satellite. and then you'd go on from there with the development of these. So this was the vision of people coming out of the Apollo era, coming out of the space shuttle era, is that you would do solar power satellites like you did Apollo. There'd be a single huge system, and there'd be a single huge project in which all of these things would be developed. This did not go forward, of course. This was this programmatic strategy and the very large price tag and the technical challenges were overwhelmed in 1980-81 by both the political opposition of people who didn't want to see this idea pursued and by the fact that the oil embargo was over. The U.S. had come up with new priorities for space, i.e. go do a space station and so on. In the 1990s, space solar power systems concepts were re-examined, beginning with a study in the US called the Fresh Look study. And these systems were, in their conception, radically different than the system concepts of the 1970s. They were far more modular. They involved smaller pieces, frankly, a much higher reliance on automation, and with a few key elements, like for example in this concept which is known as the sun tower, this backbone which would carry the power from all of these individual modular solar collectors down to the transmitter, which you can just barely see at the base, which would then send the power to Earth. And also a variety of in-space applications were identified, whereas previously in this conception, in this project, there really was no money, there were no off-ramps to use the advances that were being made to go and do something like a colony on the moon or missions to Mars. Well, in the 90s, we added a very strong flavor of saying, well, if we're going to develop these affordable, modular, multi-megawatt solar power systems, we can use them to do all sorts of very ambitious things in space. And this was the roadmap that came out, the programmatic strategy that came out of those studies and that activity. And it is similarly modular, and it had a series of off-ramps. But the central feature here was that because of these integrated features and these different applications, every 5 years or so, there would be a major, the concept was, there would be a major system level demonstration. First at about 100 kilowatts, then at about a megawatt, then at 10 megawatts, then at 100 megawatts, and so on. And that these demonstrations would be tailored so that they would support other ambitious space goals, like solar electric vehicles to take missions to the outer planets, or human-class vehicles to go to Mars, and so on. Now, this was by far more tractable, and in the review, this was taken to the National Research Council. In the review that they did of this roadmap as opposed to this roadmap, they came back and said the first few years look tractable, the money looks reasonable, and you get all of these other system applications which are wildly beneficial for our future in space. We don't know whether or not you ever get to a profitable solar power satellite, because they didn't have the scope to look at that in detail, and we didn't present it to them in detail in this road mapping effort. But they said this is a roadmap that could be done. But a feature of this was that because you had these periodic re-engineering sort of from the technology up, it was very heavily phased. So you couldn't jump ahead to this phase without doing this one and the one before, and so on and so on. Because you had to re-engineer the power management and distribution and the key architectural elements like how you assembled it and so on. Today, I believe there are far more tractable system concepts, and they lead to very much different programmatic strategies. This is one such concept. It's the SPS Alpha. I'm going to be talking about it more this afternoon. It involves a series of small pieces, propulsion module, robotics, small sat, solar arrays, wireless power transmission systems, and so on, all of which are put together to make the solar power satellite in the same way that a colony of ants, it comprises thousands of individual ants, but together they are a superorganism. So if you think of a small ecosystem in space with these organisms, that is this concept for a solar power satellite. And as I said, I'm not going to go into details at the moment because that's the topic of this afternoon's talk, but the central point being that this architectural approach, which I should say has been championed by, as an approach, has been championed by Professor Kaya for a number of years with his work on the sandwich module, which this is a variation on, avoids all of the large integrated stages that were the problem previously. And in an international assessment of space solar power that was done a number of years ago by the International Academy of Astronautics, and in more recent work that I did for NIAC on the SPS Alpha concept, the NASA Innovative Advanced Concepts Program, we found that because of this strategy, technically, that a programmatic approach, which is basically a simple progression, where you build your first versions of each of these modules and you put them together and you test them, just like you would a laptop with a number of other laptops. And then you make another one with a new version of some of the pieces and maybe new technologies, and you put that together again. But there's never any massive re-engineering of fundamental system elements like what voltage will it be at, what's the power management distribution system, because it doesn't work that way. The energy is distributed on the platform by large thin film mirrors, not by copper, not by wires. So the key elements of this roadmap include early studies, ongoing development of what are the required infrastructures, some focused technology research and development to keep making improvements, exactly the same way the electronics industry has unfolded over the last 2 decades, and a series of system-level demonstrations that involve basically the same pieces but don't radically change in their character. One of the central elements of this roadmap, and coming out of the international assessment a couple of years ago, is the idea that because of this strategy, it's possible to envision an initial solar power satellite demonstration in about a dozen years, a multi-megawatt demonstration within about a dozen years. And this is, as I'll talk about this afternoon, this is entirely accomplished because of this hyper-modular architecture, where the pieces that you're building and you're evolving weigh about 10 kilograms. You just put a lot of them together. It's like Legos in space or Tinker Toys, depending on what you played with when you were young. It's not within everybody's reach. Almost any space organization on the planet could build one or more of these piece parts. They might not do it as well as others, but there's nothing that is so expensive or unique or unusual that they couldn't do it. And as a consequence, international cooperation is central. I'd like to just highlight briefly a couple of quick notes. These studies that I mentioned and the ongoing, I'll just highlight one thing here. There is a working group under the International Academy of Astronautics for space solar power. This was formed under the auspices of the Academy a couple of years ago. It meets face-to-face twice a year, and it will be undertaking activities such as working issues of spectrum allocation, what kind of negotiations need to happen within the framework of the International Telecommunications Union. It'll be working sort of the interfaces and standards for these modules. Anybody is welcome to participate. This group is modeled on the ILIWIG, the International Lunar Exploration Working Group, or the Mars Program Advocacy Group, MPAG, I think it was called. Anyway, there are these international groups that coordinate activities having to do with various specialty fields of space science, and they do it in a way that facilitates the later creation of cooperative ventures, cooperative projects. That's the goal of the Space Solar Power Working Group. I'll just mention President Kalam, who is an honored speaker at last year's ISDC down in San Diego. He gave the evening keynote. It was quite marvelous. He has been in discussions with Mark Hopkins, who was here earlier. I don't think Mark ever has given Dr. Kalam any sake, but, but that's probably appropriate. At any event, although Dr. Kalam is not here this year, he has been very intensely involved with the current election that's just been finished in India. And the gentleman that he was supporting in that election, Modi, Mr. Modi, is very likely to be the next Prime Minister of India. And so it may very well be that that would be a good thing for discussions with India in the future. Maybe. There's been a lot of activity over the years with global media to create and sustain a global conversation. Very nice article just 2 weeks ago in Aviation Week and Space Technology, written by Frank Mooring.
And you, good job.
No, thank you. The various publications, and of course I'm plugging my book, which is The Case for Space Solar Power, which will be on sale this week, and is very reasonably priced at $9.95 for the ebook copy or $49.95 for an attractive color hardbound version with over 70 graphics. I wanted to also mention that there's an ongoing series of international meetings and events, including this one this week. Also, the International Astronautical Federation Power Symposium every year is the meeting place over the last quarter century for the space power community. And there'll be a conference next fall. In addition, periodically there's an SPS focused meeting. The most recent one was just a month ago in Kobe, Japan. In fact, just a month ago today. This is the group. There's Professor Kaya. I'm over there. And there's Mark Hopkins and a very interesting crowd of characters, cast of characters. I will mention that, and this was the instance that Mark was alluding to and talking about how Professor Kaya is very skilled at rounding up lost foreigners. We went out on a tour of Kyoto at the meeting, and it was quite challenging to keep everybody together because the people kept wandering off. Oh, I'll just go look at this in the midst of 5,000 tourists because it was springtime in Kyoto, and so just at the end of the Cherry Blossom Festival.
Don't forget.
Oh, yes, absolutely. Oh, I haven't seen it.
Oh, you got it.
No, I haven't seen it yet.
IEEE Spectrum.
Oh, that's right. Outstanding. No, I haven't seen it yet. Professor Sasaki has a nice article in the IEEE Spectrum just this last month, which is very nice. A key element of this international symposium, and it was really facilitated by the fact that we had about 30 attendees. The last day, in the morning of the last day, we had about a 3-hour brainstorming session that was organized into 3 major topics. The first were technical challenges and opportunities. The second was legal challenges and regulatory issues. And the third was media and communications. And while we worked through the first one, we talked about what was necessary for the next 2 and how technical activities supported the latter. And then when we moved to the second one, regulatory and so on, then we also fed backwards and forwards. And so we ended up at the end of this discussion with a very nice synthetic view of what are the things that need to be done, both technically from the standpoint of legal and regulatory policy, and in terms of media and outreach communications. The proceedings for this event should be coming out in the next couple of weeks. They're virtually done, and I'm assuming that we'll have no trouble getting them posted on the NSS website. So you're here today for the Space Solar Power track. It's over 2 days, today and tomorrow. It's a very strong program, roughly 24 talks, either in person or virtually, from key leaders in the field of space solar power around the planet. And it was organized principally by this track, and the sessions were organized principally by Gary Barnhart. So a round of applause for Gary, please. was kind enough to keep my name on the tracks, just for appearance's sake. I did a little bit, but very, very small. It was almost entirely Gary. We have a few special events, which will also be included. Panel discussion tomorrow afternoon, the book signing, and tomorrow on Saturday afternoon, and Saturday evening's keynote address. The gala at the gala will be on space solar power. If you're interested, and depending on how you balance the time, tomorrow afternoon I'm going to be doing a talk on the policy issues associated with space solar power, in the space policy track. And I'll be presenting a number of the findings and results from the Kobe meeting, from the space policy discussion there. With that, I'm done. Gary, do you want to say anything introductory? Thank you.
I'd like to thank everyone for coming here and remind you all that the Friday afternoon discussion is intended to revisit this notion that I was told by a collection of heretics at Goddard was the norm at NASA. An industry day was supposed to be instead of a session where you had managers get up and throw up PERT charts and Gantt charts and explain that their procurements were on track. An industry day is where the technical folks in charge got up and said, this is where our problems are. This is where we need help. This is what we've got. These are the boulders that we have to get moving in order to get things done. I hope that you can all participate in that discussion, and it's our intention that these workshops and tracks are continually moving the boulders forward to get real things done. Thank you all for being here.
Are there going to be questions at the end of anyone's talk?
Because
I know we don't have much
The intention is yes. Some speakers will do better about it than others. I would like to see people roll with it. Try and leave some significant time for questions. That's also why we built in a multiple-hour session on Friday as well.
Okay, great. Thank you.
If you wanted to ask a question, I'd be happy to answer.
Yeah, actually, I noticed your alpha chart for the schedule. That looked like a great way to reduce the TRL levels.
Oh, absolutely.
I mean, and plus you have a plan B built in and a plan C right on your chart.
Yeah.
Most people don't look at it that way, but I noticed it right
Yeah.
away.
No, absolutely. Well, and it's like these things.
Yeah.
So this was the state of the art 8 years ago. It's a
Yeah.
1 gig drive.
How much was that?
10
years ago?
Oh, it was probably $25, $40 for 1 gigabyte.
No, I mean 10
Oh,
years ago.
oh no,
it
no.
cost.
But then of course now it went from 1 gig to 2, 4, 8, 16. Now it's 32 gig. It's the same USB port. Now they've got a USB 2. It's a little faster, but fundamentally the same interfaces and standards. And so this strategy for consumer electronics is the same kind of strategy for these hypermodular architectures.
Yeah, very well done.
So anybody can make an improvement in the solar array, and it just plugs in.
And we can 3D print those up in space someday.
Absolutely. Okay.
Good job.
Our next speaker is Paul Werbos. Paul, are you here in which capacity are you, should you be introduced as?